All right, Unit 5 is talking about statistics. Statistics is actually extremely important in the medical fields for a lot of reasons. One is your tracking and funding and stuff like that. Your statistics keep track of your success rates and things like that. When you go to a doctor, they'll say, well, you have these different options. The historical success rate of this option is 82% or whatever. This option is 61% or whatever that is. Um, I mean, all that stuff is kept track of and it's listed. Also, for any sort of grants and things like that for funding, you have to keep track of statistics and prove that you've done something worthy of whatever that is. Um, Quality control within a medical field. 25 years ago, quality control was something that was done in industry and manufacturing. And more so lately, it's made its way about 17, 18 years ago, you started to see it make its way into the medical field of even as far out as the reception desk of a phone call comes in, what's the average time, how many average number of rings before it's answered, what percentage of phone calls end up going to voicemail and not being answered, things like that. Then there's the more obvious ones, the more in-depth ones like drug testing and things like that of comparing if there's a new procedure or new treatment, new medication, is it effective compared to the old medication and all that. We're not going to get nearly that far into it. Obviously, in about 2 hours worth of class, we're just going to touch on the surface. We could really spend a full 2 semesters on statistics. But it's an important part of the class because any of you going on to your, for in the nursing program, going on to a bachelor's degree, will have to take statistics at some point. So let's take a look at some of the basics. So when we're talking about statistics, there's 2 branches of statistics. There is descriptive statistics. And in descriptive statistics, all we're really looking at is to summarize. This is what we were talking about before of using the statistics to what's the historical success rate of this procedure or this medication, whatever, to compare. Really all it is just describing it, descriptive. Inferential statistics is where we actually put the statistics to use. We can use it to make a decision. This would be like formal hypothesis testing. Is this new medication as effective or more effective than the old one, or is it lesser effective than the currently accepted medication? It can also be used for, descriptive statistics can be used for tracking, but it can be used for quality checks. And this is where the line between descriptive and inferential kind of blurs a little bit, because your descriptive statistics, you're going to keep track of that data over time. But looking at the descriptive statistics, at some point, if there's a discrepancy or something unusual in the descriptive statistics, that's where the inferential part of it comes in of now you have to make that decision. Is something going on here that we need to look at or whatever? So usually one leads to the other. The descriptive statistics leads into the inferential, or you have to use descriptive statistics to make your decision in the inferential side of things. What we're going to be looking at is mostly descriptive. We're going to kind of get up to that border of the inferential statistics a little bit, kind of hint at some of the things that can be done. The way I put it is we're making judgments, not decisions. We're not doing formal decision-making processes of comparing, but we're using, okay, we can use different strategies to compare numbers and make a judgment on it, but not a formal decision or hypothesis test. So outside of those 2 branches, within the descriptive statistics, we've got to start looking at some vocabulary. And the first thing you need to define in any sort of statistics is a population. A population is a group, whether it's people or items of some other sort, it's a group that you want to learn about. sometimes called a group of interest or whatever. Usually it's the population of interest is the term used, but it's basically, for example, a lot of times political surveys are done. There's a lot of statistics in politics and government. If you want to try to do a survey to figure out who is most likely going to get the Democratic nomination for president. Well, your population there is not the candidates for president. You want to learn which one of them is going to get the nomination, but they're not necessarily who you want to learn about. Who you really want to learn about is the voters, the people that are going to vote for them, because they're the ones that are going to determine that. So your population would be all people who are going to vote in the Democratic primary elections. Within that population, we usually choose a sample. Only if we have a really small population do we ever work with the whole population. For example, if I wanted to determine the average score in this course right now, well, there's only, between the 4 locations, there's only like 15 or 16 people. I can do that. I can gather all that information. I can find that. If I wanted to learn the average income of every person in the United States, I'm not going to get, 320 some million people in the United States, approximately 270 million of them are of working age. I'm not going to take that time to gather information from all of them. So a sample is a subgroup or a smaller group from the population. If I gather information about a population, that information is called a parameter. So a parameter is just information about a population. If I gather information from a sample, or gather data from a sample and collect information, that is called a statistic. A lot of people are surprised by this. Well, when we're studying or calling the course statistics, wouldn't you want to be studying the whole population? Well, again, it's not very practical. Why do we look at statistics and samples rather than parameters and populations? There's a lot of reasons why we look at samples. We talked about the voters, or the size is just prohibitive for a lot of reasons. One reason would be time. For going back to that voting thing, the time it would take me to survey every possible person that might vote in the Democratic primary, first of all, determining who they are is going to be tough. That's an extra second thing. But the time would be just unreal. It would take years to get to everybody. Second, difficult to determine the whole population. The third is money. It's expensive. Every person you call or send a survey to in the mail or whatever costs something. And you usually have a limited budget. You can't afford to do that. Now this is a big one. It's hard to put into a brief word, but changes over time. In statistics, we're looking usually for a snapshot. What I mean by that is we want to gather that information rather quickly so that we have that picture. If I wanted to start gathering information about, again, the Democratic primary, what candidate's going to win, if it's going to take me several weeks to gather that information, well, let's say I start surveying, let's say I survey Richard here and see who he's going to vote for. Well, 2 days from now, let's say a huge scandal comes out about one of the candidates. And I keep surveying people, and, well, Richard, who was the first person I surveyed, may have changed his mind based on that new information. His vote would not be the same. And some of the people I surveyed at the end, I'm surveying them under different conditions than I surveyed Richard on, the first people, because this new information came out. So you need to get it done in a short enough period of time so that no changes occur, so that you're actually surveying the same population. When that piece of information came out, that political scandal in this example, the population changed. There was new conditions. That's one of the most difficult things in statistics is controlling conditions. If you're doing a statistical experiment in a laboratory like drug testing, you can control many of the conditions. But outside of the laboratory, in the real world, there's a lot of variables. Most of the variables are outside your control. Even in the laboratory in drug testing, it's awful tough to control because you might have somebody whose diet is horrible and whatever. Well, and it happens all the time where someone passes away during a drug trial and you exclude them from the trial because their death was not based on what it was you were actually studying. So they didn't die from the condition you were treating. They died from maybe that a heart failure due to poor diet, or if they're in a car accident or whatever. So there's a lot of stuff outside your control all the time. So the shorter period of time you can gather that information, the less chance there is that something changes and really interferes with your accuracy. Now this next one isn't terribly applicable in the medical fields, hopefully. I'm just going to call it destructive test. This is more so in manufacturing than in medical. Let's say I have a part that has to have a certain strength to be safe. Maybe I'm looking at a reinforcing bar for the roll cage of a car. Well, we produce it, and I'm going to take it to a machine, and I'm going to test it. Well, how am I going to test it? Well, I'm going to apply force to it until it breaks to see how strong it is. And if it takes more than a certain amount of force to break it, well, then it meets my conditions. Obviously, there it wouldn't be practical to test every part because the test destroys it. So if we test them all, there's nothing left to put into the car. So we take a random sample so that we can feel relatively safe. If all of these pass the test, then the other ones should be good enough as well. And of course, there are a lot of other reasons why we would take samples versus surveying the whole, or gathering information from the whole population. But we're just going to keep with those few. Now, I keep mentioning this word survey, and you probably have noticed I pull back. A survey is gathering information from a sample. If I'm gathering information from a population, and you've probably all heard this word before, it is called a census. You've heard the government census? Well, the government census is not really a true census because they don't get everybody, but it is an attempt to gather information from the whole population of the country. Okay, now, when we're taking those samples, it's very important that we gather what's called a representative sample. A representative sample just means that it represents the whole population. For example, let's say that I'm going to take a sample of 100 students. And I'm going to survey to determine whether they're full-time or part-time. Okay. And let's say that of all students, and we may not necessarily know this when we do the survey. That's the problem, is we don't know the information about the population. We're using the sample to try to determine that. But let's say of the full population of students, 68% are full-time. But in our sample here of 100 students, we get 86 out of 100. For those of you doing the numbers in your head, of course, 86 out of 100 is 86%. Would that be a good representative sample of that population? Well, not really, because that's quite a ways away from the 68%. Now, when we take that sample, because we know it's not going to be exact, we would not expect exactly 68 students out of 100, or exactly 68% in our sample to match the population. We don't expect the sample to be perfect, but we expect to be good enough. That's, again, on the inferential side, we would discuss, well, how close does it have to be to the actual population parameter before we would consider it to be a good sample? And there's a lot of discussion there that we're not going to get into. The biggest determining factor, there's two factors. One is sample size. If I go out and survey, WITC right now has something like 1,100 full-time students between the 4 campuses, or 1,100 total students, not full-time. 1,100 total students is between the 4 campuses. If I wanted to learn something about those 1,100 students, if I went out and surveyed the next 10 people I saw in the hallway, would that be a good sample? No, it wouldn't be, for 2 reasons. One, it's very small. Now, we're not going to get into how big it has to be. Different textbooks, different people have different suggestions on this. Some of them suggest it should be at least 5% of the population, or if the population is huge, it should be at least 5%, or at least a certain number, minimum number, if it's a huge population. We're not going to get into that, but you can't go out and survey 5 people either and say that's good. The second reason why my sample here would not be good if I just walked out in the hallway and surveyed the next 10 people is my sampling method. The sampling method needs... Hey, Wayne. Okay, so that sampling method, we said it has to be random. Random means that each member of the population has an equal chance of being in the sample. If I just go out here in the hallway and I survey the next 10 people I see, there's a couple of problems with that. First of all, nobody at any of the other campuses has a chance of being in that sample. Second of all, only people that have Friday classes. Anybody who doesn't have class on Friday mornings has no chance of being in that sample. So I have to determine some way of making sure that everybody not only has a chance, but has an equal chance. Probably the easiest way of choosing a random sample is just taking, for this case, we take every student's name, print them off, put it into a hat, and draw out however many it was I needed to survey. Now that's not always practical, so there are other methods that are used, but again, 2 hours, we're not going to get into, we could go for an hour and a half just on sampling practices and methods and stuff like that. Okay, so once we've drawn this sample, what we're doing is we're asking a question. And it may not be an obvious question, and not quite as obvious like who are you going to vote, or who would you vote for in the presidential primary or presidential election. That would be an obvious question. But like in drug testing, it might be survival or whatever, a cure, whatever it is we're looking at. But what's important to us is the answer to that question. And that answer is our variable. That is what we are studying. What is the average grade of a student in the class? Well, the question we're asking is, what is each student's grade? The answer is going to be their percentage or their letter grade or however we're approaching it. There are 2 types of data we can gather based on that. There's categorical. In this case, the answer to that question would put you in a category. Who are you going to vote for? Candidate A, B, or C? They put you in that category of that candidate. All yes or no questions are categorical. Do you approve of the proposal to raise taxes for school funding or whatever? Yes, puts you in the yes category. No, obviously in the no category. The second type is numerical. Obviously here then the answer to that question would be a number. How tall are you? Age, years of experience, annual income, stuff like that. Those are all numerical. How many cars do you own? How many classes are you taking? How many credits do you have? That answer is a number. Now that doesn't mean that numbers aren't involved in categorical data. There are a lot of numbers there, and there's numerical analysis that's done with it all the time. It's just the answer to the question is not a number. The numerical data gets split into two different types. Discrete, which is the easiest to work with. Discrete is counting. How many cars do you own? How many credits are you taking? You can't take 14 and a half credits. You're taking 14 or 15. You can count the number of credits you're taking. You can count the number of cars you own. Then there's something called continuous numbers. Continuous is a measurement. Height. Trying to think of others. Height, length, things like that. Weight is a measurement. There are some things that kind of fall in a gray area between continuous and discrete, like annual income. Well, you could count how many cents you earn in a year, how many dollars you earn in a year. Is it a measurement? I mean, there's other definitions of continuous and discrete, like continuous, there's no space between any two consecutive numbers, or no matter how close two numbers are, there's always a possibility of somebody being in between them. Obviously with money, that's not the case, because between $37.52 and $37.53, you can't be in between them. But you know, mathematically you could, but just because of the physical properties of money, you can't. So that one, money is usually a toss-up there. It generally falls in discrete if you argue it out. But there are some there that are not so obvious. So our next step is we're going to talk about working with the data. Categorical data is pretty simple to work with. With categorical data, we're generally talking about a proportion or proportions. Categorical data is usually most useful when you break it down, break the answer to that question down to two things. We put you into two categories, A or B. Yes or no usually is how we classify. So instead of saying who would you vote for in the presidential election, would you vote for candidate A? Yes or no. So any other candidate puts you in one category, candidate A puts you in this category. But it is possible to have more than two categories there. It's just usually easier to analyze. For example, let's say that out of 200 people surveyed, 52 support candidate A. That gives us a proportion. Now, proportion is a percent as a decimal. What that means is we don't have to put it over 100. We just divide it out. 52 divided by 200 is going to be 0.26. That would be 26%, but as a proportion, you just leave it as 0.26. Often when you're stating this for the consumer or for the general public, you would turn it into a percent, because people, even though it's the exact same thing, if you state a proportion of 0.26 support this candidate, people don't know what that means. We say 26% of voters support this candidate. That's usually a little bit more clear for the general population. That's really all there is for summarizing categorical data. I mean, getting the inferential side of it, there's a lot of things you can do with it, but we're not going there. So we're going to spend most of the next hour and a half on numerical data. To understand numerical data, you have to understand something called a distribution. A distribution is just a plot of how popular, how common certain values are. If we're looking at discrete numbers, we'll do this. Let's look at test scores. So let's start out at 60%. And work our way up. So from 60 to 100, we're looking at that range. Let's say all scores have fallen within that range. And let's say we're looking through, well, that line isn't even close to straight, is it? But anyway, pretend that line's straight. Let's say we're going through, okay, the first test is a score of 77, so we're going to put a dot there. And there's maybe 84, and 81, and another 77, and a 71, and a 79, and maybe a 92, and then another 79, and an 82, and another 81, and another 79. And we just build these dots up. And you can see as we put these dots in here, it kind of rises. The most common numbers rise up with the dots building up. And as you keep putting in those dots, as you have more and more data points to put in here, it creates a shape. And that shape is the distribution. In nature, that distribution tends to take on, most of the time, a shape similar to this. Many of us heard it referred to as the bell curve, right? Its technical name is called a normal distribution or a normal curve. Now looking at this, let's say I have 87 here, or 82. Would I expect more students to have a score of 87 or 82 according to this curve? 82, yeah, it's much higher here than it is here, isn't it? The height of the curve determines how many, it doesn't determine, it shows how many people we would expect to have that score. So obviously 70 would expect to have less people that had a score of 70 because the curve is lower there. Well, that's what the distribution is. Now there's two things that we can describe this distribution. If we wanted to summarize it numerically, we would have to describe the center. Now the center for a bell curve is at the highest point here. If I cut the bell curve straight down to the highest point, which appears to be at 80 here, it should be symmetrical, or the exact same shape, just a mirror image on one side to the other. Now I drew this poorly, so mine isn't, but imagine that it is. That should be in the middle of the data. That is the center of the data. The other thing we measure is the width, or the spread. And that's a little bit more difficult to judge. But you can tell here the width, the spread of this one, it's kind of meaningless unless I compare it to something else. Let me draw another one in. Let's compare it to this one. Which curve has more spread, the black curve or the brown curve? The black one. The black one is much wider. The brown curve is much narrower. So we would say the brown curve has less spread, a smaller spread. However, the center is exactly the same. They both have the same center. I could draw another curve here. Has approximately the same spread as the brown curve, but its center is different. Now its center is moved up here. Does that make sense? So if we can adequately describe the center and spread of a curve, we can do a pretty good job of summarizing it. So let's talk about describing the center first. There are 3 or 4 values we use to describe center. There's 3 main ones, 2 that are the most common, but I'm going to add in a 4th one because it does get used in the medical fields. The first one is the mean. The mean is the one that most of us learned back in grade school, and we called it an average. You sum the numbers. Now let's add up the numbers. And you divide by n. Now, n is the number of items in the sample. When we're doing the average, if you had 4 numbers, you divide it by 4. If you had 7 numbers, you divide it by 7, and so on. The next measure of center is the median. The median is the middle. Now, we said center is supposed to be the middle. All of these are supposed to kind of measure the middle. Well, median is physically and numerically in the middle. If you put the numbers in order from smallest to largest, the median would be the number at the very middle of that line. And we're going to look at ways of finding the median in a little bit. We have to find its location, and then we find the value that's in that location. The third method is something called the mode. The mode is the number that occurs most often. There are several data sets that don't have a mode. There might be a data set where no number is ever repeated twice. Especially if you're measuring height, because if you're taking it down to, let's say, the 10th of an inch or even 100th of an inch, chances of 2 people in a relatively small sample having the exact same height are fairly small. So there might not be a mode. Or there might be, like for your number of credits, there might be 20 people that have 16 credits and 20 people that have 14 credits. And everybody else is less than that. Well, there's 2 modes, and some textbooks, some theories allow you to have more than one mode. Bimodal, they would call it. Or depending on the size, if you have a bigger sample, you can have even more than 2. For our purposes, there's either one mode or no mode. You know, if there's 2 different numbers that appear the most often, then we don't have a mode. Not the most reliable one. It's pretty easy for unusual values to appear more often. Then there's something called the mid-range. The mid-range is statistically not really precise, but it is quick and dirty. It requires us to define a couple of other terms. The mid-range requires us to take the maximum, the max, which is the largest number, and the minimum, or the min, which is the smallest number in the list, and just average them together. Add them together and divide by 2. Now, when you're doing this on your calculator, the same with the mean, by the way. You're adding up these numbers. Before you divide, what should you do? Hit equals. Hit equals before you type in divided by whatever. Otherwise, order of operations takes over and it divides the last number in the list before it adds them all together. So make sure you hit equals so that they add them up before you do any division. So let's do some examples of this. So I'm going to do a couple of different sets of numbers. My first set of numbers here, let's do that one. Oops, come on. I'm just going to slide this over a little bit because I wrote bigger than I wanted to. My second set of numbers, so like that. Now you'll notice a similarity between those 2 sets. They're the same set, I just added an extra number to the second one. There's going to be an obvious reason in a little bit why I did that. Let's find the mean of this first set. So we have to add that. First of all, what's n equal for this? N is how many? Yep, so 1, 2, 3, 4, 5, 6, 7, 8 is n. So we're going to add them up. 7 plus 13 plus 16 plus 19 plus 19 plus 20 plus 26 plus 32. What is that, 152? Yes, no. 152 divided by 8 is 19. All right. Okay. I thought so. So I get a mean of 19. Median. Well, we're going to have to define. First of all, these numbers are in order from smallest to largest. I did that as I wrote out the data set. So that saves us a step right there. They're already in order. If they weren't, that would be the first thing we have to do for the median, is put them in order. So step one is put them in order. Step two is to find the location. The location of the median, since the median is in the middle or halfway through the list, it is 1/2 or 0.5 times n. So for this set here, 0.5 times 8 or 4. Now that doesn't mean the fourth number is the median, but we're going to use 4 for the location. Since this is a whole number, in other words, there's no decimal or fraction there. The location of my median is between the fourth and the fifth number. If our answer to that 0.5 times n is a whole number, it's between that number and the next number is its location. So between the fourth and fifth. So going up here, 1, 2, 3, 4, 5. I'm just going to finish numbers out. Sorry. Between the fourth and fifth numbers is 19 and 19. Now obviously between 19 and 19 is 19. But if they were different, we would just add them together and divide by 2. So our median here is 19. Really quick calculation, what's our mode? 19, very good. That's the only number that appears more than once, is 19. Mid-range. What is the largest number in this set? 32. Smallest number? 7. 32 plus 7 is 39. Divided by 2 is 19.5. So slightly different than the others. The mid-range is desirable in a lot of cases because it is quick and it's easy. But I'm going to show you some reasons why it's not so desirable. Now, I've already mentioned my little bit of distaste for the mode and the median, the mid-range. So it leaves us the median and the mean as being the two main ones. The debate always comes down, or the question usually gets asked, which one's the better measure of center, the mean or the median? Well, many of us favor the mean because it's the first one we learned. We learned how to average when we were young. And it is kind of satisfying. You have this formula. You add numbers together and you divide. You're cranking out all these calculations. And since you're in a math class, you feel like you should be doing that. But is the mean really the better measure of center? Well, in a good set of data, it doesn't matter. The set of data I put up here, it was a pretty good set of data. The mean, the median, and the mode are the same number. In fact, in a good set of data, they should be the same. The middle should be the same no matter how you measure it. But if there are flaws in the data, like with my second set here, then we have to figure out which one is the better one to go with. So the mean here, if I add that up, 152, it's going to be what, 240 divided by 9, which is going to be what? 26.6, 26.7, 26.666, yeah. So 26.67, we'll call it. Well, that changed quite a bit from 19, didn't it? My median, n is now 9. So the location of my median is 0.5 times 9, or 4.5. Well, we have to make another note here. If this is a decimal, obviously 0.5 would be the only decimal we would have. Then we round up. So the fifth number in the list is my median. So 1, 2, 3, 4, 5. I'll finish numbering out. The fifth number is 19. The median is still 19. Now the mode won't change. The mode would still be 19 because that's still the number that appears most often. The mid-range would change quite a bit. 88 plus 7 is 95 divided by 2 would be 47.5. So obviously the mid-range is not a very good measure. But you can see here, when we added this one really large number here, the 88, the median didn't change at all in this case. The mean jumped by 7 2/3, a relatively big jump. In fact, if you look at this list, there's only two numbers larger than that mean of 26.67, the 32 and the 88. That's not really in the center. Statistically speaking, and I fought this when I first learned statistics because that mean to me is just so satisfying to have that formula. I've been doing it since 3rd or 4th grade. But statistically speaking, the median is generally accepted to be a better measure of center. Because it's more stable, that one unusual value doesn't throw it off. Let me give you an example of why that is, or how that can come into play. I believe it was 1982 or 1983. We're going to just say 1983, about. University of Virginia. Advertised. A graduate in that year, graduates in their 4-year marketing program, 4-year marketing degree, made an average starting salary of just over $78,000 per year. Now, right now, if somebody offered you $78,000 per year, would you be out of here and take it? Yeah, good chance you would be, right? That's pretty good money now. To put some perspective on it, in 1983, the average starting salary of a high school teacher was between $16,000 and $17,000 a year. So $78,000 was a really good starting salary. Is it true? Yeah, it's a true statistic. But is it accurate? Is it misleading? It's extremely misleading. Why? Well, one thing that they left out of that statement is that one of the graduates that year, and he did graduate, he completed his degree, and he graduated with a degree, a bachelor's degree in marketing. It was a man by the name of Ralph Sampson. Those of you that are NBA fans would know that Mr. Sampson was 7'2", and in both his junior and senior year, he was a 2-time NCAA Player of the Year, led his team to the NCAA Finals in the tournament twice, lost once, won once, and was the first player drafted in the NBA draft by the Houston Rockets. He signed a multi-million-dollar contract, but he was still a marketing graduate. Now, do you know how many $18,000 to $20,000 a year marketing graduates it takes to average a multi-million-dollar a year contract down to $78,000? We're talking a couple hundred of them. In fact, Mr. Sampson was the only one in that group to make over, I believe it was $37,000 if I remember the numbers right. One other person made $37,000. That was the next highest one. So he was the only person in that group that made over that $78,000. Obviously, this was the mean. The median for that set was around $23,000. Now, if you were going to that school, which number would you rather have them advertise to you? Do you have much chance of doing at or better than $78,000? No, you don't. Do you have much chance of making at or better than $23,000? You do. Anybody tell me what chance they did have? What percent chance they have of making that much or more? The median falls where in the data? Exactly. The median is in the middle, exactly in the middle. So you got a 50-50 shot of making more or less than $23,000 a year. Okay, it's about time for our break. So it's 11:18 right now. Let's come back at 11:28.